beautiful Saturday, and so let me introduce our speaker, Anthony. So I'm honored to have Anthony to be to be a speaker today. Anthony is a data scientist with a control and system theory background, and he is working on change tracking topic modeling for Wikipedia. And he also has his own venture, which you're about to hear, the fifth programming, which is the programming language, which is the project, and maybe turn to something very exciting. And he is also writing a book. This book is about essential computer vision with language.
Lauren Barwood is she's actually knows the most about the computer vision stuff.
Oh yeah, with Lauren.
Yeah, no problem.
And so yeah, he is also a board member of the Counterculture Labs in Oakland. So let's welcome Anthony.
All right, thanks a lot, Lily, and thanks to Kelly for inviting me. Can anyone hear me fine if I speak like this from here? Is that good?
No, quieter.
Okay. Is that better? Okay. All right. So here is this little bit of an ambitious title, I guess, from statistics to deep learning and beyond. So I think quickly we'll get a better sense of what I'm talking about. But first, just to frame things, this is a pretty open-ended talk. It's not really about results that are set as much as research that is yet to be done and old questions that we can revisit with new tools that we have now and what we might be able to do with that. So it's going to be not just technical, but historical and anecdotal, and there's a lot of things that I'm going to be talking about at a very high level, and I don't want anyone to be baffled. I specifically do not want you to be baffled. So if you want to ask a question or if you have a comment about something, please just feel free to jump in at any time. So here is kind of the technical framing of what I'm trying to talk about. So I'm going to in just a few more slides I'm going to situate this in a little bit of like the intellectual and philosophical history, but right now I just want to talk about like the technical aspects of these distinctions that I'm trying to draw. So let's just kind of speak at a very conceptual, stereotypical way about these three paradigms and what's distinctive about them, and how they, eventually I want to build towards how they might fill in for some of each other's weaknesses. But so in statistics, you basically start off by counting events, and then you come up with some assumptions that lets you frame the situation in terms of probability theory, and you interpret your data in that way. Most of the techniques come from pretty strong assumptions on the kinds of uncertainty that you're dealing with. They work best in low-dimensional settings or settings where you have the independent, identically distributed finite variance central limit theorem to rely on. Typically at a single scale, and a lot of the structures that it borrows from or builds on probability theory to do its work are discrete and continuous low-dimensional distributions. Deep learning is one approach that is trying to relax some of these assumptions and go beyond them in a certain way. So this is mostly conceptual here, but I want to take this as a certain definition of a feature. I'm going to say it's a pattern of joint variation, but it isn't really making distributional assumption, and it might actually be pulling that pattern out of a sparser or a higher dimensional space of joint variation. And as for a theory of information, a lot of neural networks don't explicitly have one. So it's ad hoc, it's like a continuous output. Often what you'll do as a post-processing step is you'll interpret those as probabilities or something, but it's not really built into the internals of how things works necessarily. There is a little bit of ad hoc recursion that's going on in deep learning, which is a lot of what makes it deep, is that now you're recursively composing these things, and that lets you get a multi-scale structure. And so, yeah, I've basically said all of this already. And so now what do I think might be beyond them is, and this is also, we're going to see a little bit of the symbolicist connectionist divide, and I think what might be beyond is to bridge this divide and combine the strengths of both approaches now that we have really well-developed tools for addressing both sides of it. So now we might be able to actually bring general recursion back into the picture. And so in recursion, formal languages, programming languages, loosely speaking, we're working with composition rules, let's call them grammars. So we define those, we try to infer them, we generate them. For the most part, this is built in discrete terms and on top of Boolean logic. And so that's one of the things that has actually been very limiting to this paradigm that we might try to move past. There's a deep ability to deal with process here, so that's basically a really deeply nested sequence of conditional dependencies, and that's something that, to put it in statistics terms, that's something that is very challenging on the statistics side, and most of statistics is actually built on assuming that away, and when you don't assume it away, you get things like partially observable markup decision processes, which are some of the more difficult things to deal with. And so what we see here is a lot of discrete combinatorial variation. So that's kind of the roadmap of the ideas, the technical ideas. And so I'd also like to talk a little bit about the historical and philosophical context around the development of these technical tools. So in early computing, you had some, let's say we're back in the 1920s and going on into the 40s and the 50s. Cybernetics is actually a major force in speculating about and starting to define what computing tools might look like. And cybernetics is roughly the Greek term for the guy steering the boat to keep the course in the turbulent waters that are pushing the boat around. So there's this uncertain environment, and there's an agent in charge of the system that is trying to adapt the control inputs of the system to deal with the uncertain environment and to apply information feedback to the determinant of control to guide the system along a trajectory that's desired towards a desired goal, maybe. And that is that's related to another framing issue that happens in logic and computer science, which is non-determinism versus determinism. So the cybernetic perspective, I think, puts the emphasis on this non-deterministic environment and non-deterministic ways of dealing with it that are constrained by certain more or less desired states, but the way that you get there is left open-ended until you're actually getting information from the environment. Versus something that's deterministic or mechanistic, which, as I'm going to say shortly, ended up dominating a lot of how software tools are built and work now, is that there is this mechanism, and it is as deterministic as you can possibly make it a priori, and it just you know as much as possible as you can about how it's going to work ahead of time. You leave as few degrees of freedom as you can until the end, and that lets you make really strong statements about how it works. And so that's like, that I think is essentially what has become functional programming now, is the desire to do that. And this is, there are actually some ideas in systems theory now that I think are important for thinking about this. One is the idea of the bow tie. So it's, imagine that you've, like here's your environment, and there's all of this, complexity and uncertainty in the environment. So you have this big state space that you could be in, and there's a lot of uncertainty about where you are in it, and then your agent is in the middle, and your agent has a certain finite capacity for modeling that and for producing actions that can then go on to influence the environment again. And this is also, ideally as broad a space of actions as you can possibly represent and generate, because that feeds back into here and constrains the environment in turn. So, and there's this idea of the law of requisite variety, which is that this bottleneck of how much variety, you could think of it in information theory terms of how a priori constrained this agent is. That is an important limit on how many different kinds of environments it can deal with effectively by generating the appropriate actions. So already from this perspective, it's a little bit alarming that we're trying to apply really strong a priori constraints on how our systems work. And this is actually a rather old and perennial controversy. So it reminds me of things that have happened in cultural contexts and political contexts over the years. Like there's the rise of legalism in ancient China, which was one of the key ideas of that was that, and it was a response to this to the preceding period in history, which was the 1,000 schools of thought, where you had all of these different competing philosophies, and politically things were very decentralized. You had all of these warring states, these principalities who were in intense competition among themselves. But then, a little before, around 250 BC, everything was unified under the Qin emperor, and then legalism became the philosophy that regime imposed, and that was that the subject should not know what the intentions of the ruler are. They should not try to come to their own conclusions about how to serve those intentions. They should just follow the orders that they are given. And that was like the essential idea of how you maintain absolute power, but it's also really restricting the variety that these agents have to cope with their environments. And again, around 19th century in the West, in America, we have substantive ideas of justice yielding to procedural ideas. So this is in the law now, and it's a shift from judges in interpreting the law focusing on what the desired outcome is and using whatever means they need to get to that, to shifting to just considering in a lot of ways a more well-determined problem of were the appropriate procedures followed, and the outcome is now secondary. So now we kind of have this mechanistic idea of how law works, and the similar things going on in industry with Taylorism, where we're saying, we don't have to have like these artisans figuring out how to make things. We just need like a standard process, and we need to get the workers to follow everything very efficiently and go through this a priori determined process. And then this is also playing out in the military at almost the same time. So there's this was actually an important advantage that the German army had in the Blitzkrieg, and they had this idea of Auftrag's tactic, which was giving a lot of autonomy to the lower level commanders, and this was very different from this kind of industrial model of command and control that their opponents were more bound by. And everyone kind of talks about the tanks and the blitzkrieg. This was actually another advantage they had, was that they actually had this philosophy of giving more agency lower in the hierarchy. So then you know, a lot of early computing is happening in this military context, of course, where a lot of physical sciences are being used to develop weapons, for instance, and we see that the cybernetic philosophy, which is also very useful for weapons, and if you want to make a guided missile, that's kind of how you do it. But for a lot of other things, it is actually yielding to a more a priori logical idea of how computing should work. So I think you know, the way I interpret the idea of the Turing machine is it's looking at what rooms full of human computers are doing, and it's trying to eliminate the arbitrary kind of subjective element of what the person is doing in their head to figure out what mathematical steps to do next, so that you can then completely determine that and get it to run on a machine. So the head of, you know, the tape of the Turing machine is basically the piece of paper that the human is writing on, and then the head of the Turing machine with its state is this thing that you can't look into if it's a human, but if you formalize it, then now it's got completely deterministic dynamics, and now you have a Turing machine. So so then cybernetics basically becomes control theory, which starts to limit itself to just the mathematically tractable part of the broader range of problems that it was considering before. So a big milestone in that is you get the Kalman filter. So many of you might be familiar with that. It's used to train recurrent neural networks, among a lot of other things. But that's basically the linear quadratic error version of a much more general thing called the particle filter. So the Kalman filter, you just have a linear system dynamics, you have Gaussian errors, and you have a quadratic error criterion, and then you're able to do the math and figure out exactly how it should work. But the more general version of that is the particle filter, where you just have samples from a distribution, and it could be, you know, any distribution that you could estimate that way, and then you propagate them through the dynamics. And this is something that it's hard to imagine dealing well with how really nice computers like we have now. But back then, you know, the compromise was probably the right one. But this is something, you know, this is maybe the first example of something that is the sort of thing we could revisit now. And then also in the logical, in logic, we have people going further, developing type theory and going further, applying it to programming languages. And type theory is basically set theory where you eliminate the possibility of cycles in your definitions. And you'll note that a lot of what complexity and cybernetic control theory is concerned with is the effect of feedback loops. So now we've kind of changed our formalism so that we can make a priori statements about completeness and consistency, but we've lost a little bit of modeling power because we can't actually go through dynamics using this abstraction anymore if there are any circularities in them. So things are starting to bifurcate. And this set the stage for the 80s, where we actually have a lot of very diverse language and hardware research, and then the personal computer comes in and creates a lot of economic incentives for standardization around things that will run on very low-end hardware. And so I think we're still kind of trying to recover from that event where a lot of these roads that people were trying to take suddenly had a lot less economic support for exploring them. So notably in that scene, Planner was a programming language that Carl Hewitt was quite involved in. He was also behind the actor model, which is now a big part of Erlang and Scala and many other systems. But Planner was actually doing evaluation as it says with the planner. So you represent ways that you can change the state of the computation, and then there's a general purpose planning algorithm that is figuring out how to achieve the goal that you set for it. And that involves a lot of non-deterministic search, and people don't have a very good idea of how to do that back then, so it gets gradually pared down, and now we eventually got scheme out of it, which is a completely different animal. And something similar kind of happened with Prolog, where the two defining features of Prolog were this non-deterministic search-based evaluation and unification. And then on that evolutionary branch, Icon got rid of the unification by default, but we still had this non-deterministic search using generators. And then Python got rid of that too, and it's just starting to bring generators back into the mainstream now, although it's been a part of the conversation for a long time. So Python kind of got rid of both of the main distinctive features of its ancestors. And now we're just starting to talk about deep learning as it actually impinges on the more mainstream computational problems that we face, because we have a lot of data and don't entirely know what to do with it. And that's bringing us back into this, basically this 80s era of early neural networks. So now that we've got the whole one version of the last 100 years of history, we can try to talk about statistics in this context. So let's try to define statistics, and probably this will necessarily be a bit messy, but let's call it probability theory plus hypothesis testing. And so this is kind of paying short shrift to decision theory and actuarial science and information theory and other things that are quite related, but I think this is what when someone goes to apply statistics and they've come from their university course in statistical methods and whatever their field is, this is basically what they've learned and what they're trying to do. And I think this is still a big part of what data science is now. So the way that we make a hypothesis is it is a certain logical statement concerning a certain limited form of uncertainty. So we've the next slide is going to be about this, but we kind of assume that the variation is of a certain kind, and then we have this: is it a null, or is it far enough away from the null that we're going to call it something else? And it's this kind of binary distinction that we set up. And this is there are a ton of arbitrary little things in how you could do this, and people have really never quite been able to agree on how to do it, and it's quite reductionist, and we can see a little bit more of that. And so some of the things that it doesn't really have a great way of dealing with are heavy tails, non-correlation structures, and high dimension. And those are, as we saw earlier, like some of these are things that deep learning has the potential to address. So a bit more on what I was saying before. So we're assuming some sort of a distributional form. So probably what we're doing is we're saying that the finite variance independent identity distributed central limit theorem applies. So we're getting some species of a Gaussian. And then we've under that assumption, so we've taken the universe, we've restricted it in that way, and now we're going to partition what remains, and we're going to say close to the null, far from the null, within that subspace of the universe. And just in case, I'm not going to talk about it, but if you want some interesting reading on this, here are a couple of interesting things. And also, and a little aside on this, if you have some set and you want to partition it into mutually exclusive subsets, in general, that's actually exact set cover, and that's an incomplete problem. So if we wanted to kind of generalize past this to something similar in flavor, but maybe a little bit more rigorous, that might be a little challenging. So that kind of helps you to situate this paradigm, I think. And so now we've set up the problem this way, and we're going to consider the likelihood of the data under the a priori assumed distribution, and we're going to set a threshold that rejects the null. It says we're far enough away from the null, and that's our significance threshold. And so by this idea that it partitions the universe, and that we've exhausted the whole universe that we care about, then we can conclude significance if non-significance is unlikely enough, and people just kind of randomly say this. So, and if you want to go a bit more into this controversy as it has actually played out in various research communities, there are some really good course notes by R. Chris Fraley and for his Psych 548 course at University of Illinois Chicago. So now often you're saying assume that the premises that lead to a Gaussian distribution apply, because the central limit theorem seems quite strong, when you're in this first, second year statistics course, they say the central limit theorem, but there's actually a whole family of them that apply under slightly different assumptions. But what happens when it wasn't Gaussian, but you're still pretending that it is, then everything goes into all of that extra variation that is probably in your tails now, and it's just going into pulling you further from the null. So you are getting more significant results than you ought to be. So, and then there's a little bit of arbitrary flavor in what you can do with the data. You could just, what do you, if something isn't like sitting on your Gaussian curve, it's way further out there, you kind of get to decide what you want to do with it. Do you feel like you like the null, or do you feel like you like the other one? Like, do whatever you feel like doing. Because this is something that kind of has this shadow of doubt around it because of the way the issues have been framed, and it gives you this arbitrary ability to deal with it as you please, and it helps you reject the null if you keep it. So, and actually Fisher, who was one of the main people who defined this in the first place, said that it should not be used to come to conclusions. More recently, Ioannidis has looked into some of the ways that this has played out in concrete research communities, and he has come to this conclusion that for many current scientific fields, claimed research findings may often be simply accurate measures of the prevailing bias, and there's a really interesting argument that he uses to build up that conclusion, and he's now at Stanford looking into this with the team full time. And in another area, Arbusman has found that the half-life effects in certain metafields, I believe it was hepatitis maybe, I have to look it up, but it's about 45 years. So so there's quite a lot of turnover in what knowledge is broadly accepted in the professional field over the course of someone's professional career, certainly lifetime. And then in molecular biology, there was a study where Amgen researchers were trying to reproduce some of the most significant results in the field, and they were only able to do this for about a tenth of them, 6 out of 53. So, and then here is a good paper if you want to go a little bit deeper into this, and of course there's a lot more there. If you can can go as deep as you want.
Would
Yeah.
you make these slides available?
Yeah, we'll definitely figure it out with the organizers. At the very least, I'll just post them in the meetup comments. What is, aside from the kind of technical possibility that I mentioned before, like what is going on here? The idea of peer review is actually a little bit suspect because it's prior restraint on what can be published, and we're starting to get past that with like preprint archives and open access, where the comments can come after publication and the whole process can be public, and this could help to get rid of the bias, but we still have this bias from the last 200 years of how all of this knowledge has been developed. So like positive results are more interesting than negative results usually, and reviewers have their biases, and that's a bias. And it could just be, they could be biased in all kinds of ways. They could not like certain classes of authors, or they could just have confirmation bias. They could have all kinds of biases. Another interesting historical aside, like why do we have research universities and like commercial journals? We have it because early to mid-modern imperial France and Prussia wanted to build empires and assert control over the intellectual lives of their nations. So, and that's another interesting bit of history that you can delve into. Here's another interesting paper by Gellman and Logan in 2013 on the folk idea of p-hacking and what is it and what isn't it. So a lot of people talk about researcher degrees of freedom, where there are many plausible ways that you could analyze data, and you as a researcher kind of get to choose which way you do it, and you could be actually doing your own selection process where you try multiple different ways and do the one that reports significance. And they said you don't even really need to do that and to be all paranoid and conspiratorial about this. You could just say that there's kind of data degrees of freedom, and when people get taught their methods, they're kind of taught to do pattern recognition, and they'll look at data and they'll kind of informally see what kind of analysis it matches based on how they were educated, and they'll say, okay, that's the right way to do it. I see this variation pattern informally, and I'm going to choose that, and that's going to bias things towards finding a way to frame the data that leads to a conclusion of significance. So how might we deal with that? At some level we have to figure out how to make the choice of all of these contextual assumptions explicit and automatic. So I think the furthest anyone has gone on it yet is this idea of symbolic regression, where you can search for a model that fits the data, and if we could actually put some kind of universal prior on this might lead in an interesting direction. And then of course, and this is another thing that you can go and look for and find if you're interested in it, but there are plenty of cases where there's just plain fraud in how the data is collected. Probably no method is going to do that, but it would be nice to at least be able to see if there's something fishy in the data, if there's just something that is, some really definitely strongly biased, a priori implausible thing that's going on in the data, and if the method could actually pick that out instead of kind of hiding it behind some really strong assumptions. And so this is all still a lot of what structures these methods is this assumption of independence and independently and identically distributed quantities, events. So what does this not really deal well with? If there's stateful variation over time, that is going to create this deeply nested structure of dependencies. It's state at one time, strongly constrained to the state at the next time, and it follows this trajectory. And so we have, that's basically what something like the common filter, the particle filters, is trying to deal with. But it's maybe in finance you'll get a little bit into that, but you'll probably use some more restricted stochastic process still, and that's still something that isn't really applied too widely, maybe not as widely as it should be. And then there are other reasons why you could have deeply nested dependencies other than stateful variation through time. You could have something that has to do with like influences propagating through a social network or through economic ties or whatever it might be. And those are, empirically we know that the structure of those are such that there are short paths, but there are kind of relatively few paths, and the conditional dependencies are quite strong, and that leads us to get these really heavy-tailed quantities coming out of whatever we decide to measure of them. Getting a little bit more general about this, if we have this non-trivial correlation structure, then kind of our main trick in statistics is not really very effective. We can't like find the subgroups that are more or less conditionally independent and average within them. And that's most of what we do is we kind of average within them, or we integrate something within them to get a parameter estimate. And what if the data is really sparse relative to the space that it lives in? Then like averaging and integrating just don't work very well. So there's a lot of problems with this idea of like fixing this reference point in the hypothesis space and then measuring a distance from it. Because we've got this closed world assumption behind everything that kind of says that we understand everything, how everything works. And when we don't understand it, in fact, then that kind of, and often we don't even bother checking that assumption, or we could just be dealing with a situation where even if we did check and try to fix things up, we couldn't really do it. And it's not like it's impossible to work with heavy-tailed data, but it's hard. Sometimes it's impossible. Even when it is possible, people often don't use the right method. At the very least, this requires a lot more attention, and it's not being paid. So we've kind of got this wrong distance metric that we're defining to define significance on top of, and maybe like distance from a certain point in the hypothesis space is a bit too much to assume right up front. Maybe that isn't the right paradigm. So what might be better is, what if we just tried to say what is the joint distribution and how certain am I that is the joint distribution. So try to find the pattern that we can find in the sense of a feature, and not a priori set any kind of methodology for saying whether something is significant or not. We'll just say that science is about accumulating information about joint distributions of things that we observe, and then if you want to go and draw conclusions from that of some sort, then that's up to you. Take the information that has been gathered about that and do whatever is appropriate to your specific question. And you might get something like that resembles what people do already, is that people could first say, okay, here's our attempt to model the joint distribution, and then we have this hypothesis, and then we're going to explicitly say, here's a good reason for treating the hypothesis in a certain way given this model of the joint variation, and then we get this conclusion. But there's a lot more things that need to be decided on and justified in there than just saying like make the standard assumptions and p equals 0.5. And to try to like navigate this much broader space of possibilities, like I don't think this is something you could have imagined doing in the 50s when there were not that many computers in the world, and but now we have a lot of really good non-parametric techniques, and we have these universal complexity-based or information-based priors for figuring out what in general is a plausible model versus not. And then just a little more technical information on what's going on in high dimension. So So one of the most important things that happens is that if you have your data vectors and you normalize them, they are getting closer to the unit sphere in that dimension because there are kind of fewer points in the neighborhood. The space gets sparser, so which dimensions are non-zero actually starts to carry more information than the magnitude or the distribution along each dimension, and you get exponentially more local extrema, and it starts to turn into more of a combinatorial logical problem. And so we were talking more in the beginning about how from the world of like programming languages and discrete structures and exploring them, we've actually got a little bit of a start in looking at those situations. But gradient descent and staying within the convex hull of things and stuff like that actually gets less useful. And there's this idea in the deep learning community that maybe like the error surface is waffle shaped. So there's kind of saying like, well, we could still use these gradient descent techniques that are traditional in the neural network world because, I mean, the like bad case of a high dimensional error surface, and I'm actually not too sure how to draw this, but let's say I can project the whole error surface onto one dimension, and maybe it's like this, but there's this one. This is like really low error, and there's only one of it, and it's way lower than all the rest of them. So to find that is kind of like the needle in the haystack. And how do I go about finding that? Well, probably not gradient descent, because like most of the spaces that I pick, or most of the starting points that I pick for gradient descent in this space are not going to be in this little basin of attraction here for this one. Most of them are going to be in some other one, and they're just going to lead me here or here, and that's not nearly as good as this one. But then let's say it looks like, I'll just make a one-dimensional waffle, but a two-dimensional waffle has all the little cups for syrup to go into. So here's like a one-dimensional waffle, and it's just this beautiful regular thing, and you're saying like, well, who cares where I start, because I'm just going to go to one of these, and it's the same as all the rest of them. They're all exactly as good as the rest, so I don't care which one I'm in. And so this, maybe there are problems like this, but I don't know if anyone has actually observed this empirically in any way, and you wouldn't really know for sure unless you could get some broad class of problems you were interested in and find what the global optimum was and then compare it to all the rest of them. So it's really like tabulating all of the local extrema in this space where there are exponentially many, yeah.
But you can push your
Oh yeah.
But by construction, a lot of neural network and the latent variable models have to be like this, because say there's a hidden layer in a neural network, that if you fit that model, the fit model is equivalent to any other fit where you just permute the indices of the hidden layer. Again, let's say you have a totally connected layer.
Yeah.
Then all models with permutation of the indices of the hidden layer are equivalent.
Right.
So that's an example where you have exactly this, because you have complete invariance under permutation of indices.
Right, and so that's that point right there,
Okay.
and that's a completely spurious form of regularity, because that is you didn't constrain your model class well enough to eliminate that. What you should have done is like maybe found a way to get rid of that permutation so that you're searching the meaningful part of the space instead of this one that has all of these this spurious duplication and how the parameters have their effects on the results. So, and that is also something that is that's factorial in some function of the number of parameters. So,
sort of along these lines, there's an interesting paper about a year ago by Bengio.
oh yeah, I think
one of the Bengios, I forget which one. But
yeah.
The point of it was that in very high dimensions, the problem can actually be the explosion of the number of saddle points instead of local minima. So fitting algorithms can get caught in like these really like low gradients, slowly improving inflection points, saddle points. Yeah, so if you look up saddle point
Yeah, if you, let's find that, because I think I like heard about that and lost track of it a while ago, so I don't want to lose track of it again. Okay, so that's just a little additional background. So we've had these many trains of thought that have kind of led up to deep learning. So what is deep learning? And so maybe it isn't anything in particular. It's just kind of like a clever brand or something like that. But maybe it is something. Maybe it's neural networks with more than one hidden layer. So like, what is a neural network that has more than one hidden layer? Well, maybe it's some variety of like composed function. And if you go and prove the universality of approximation of a feed-forward neural network, then that is how you're going to be treating it. You're going to apply the Stone-Weierstrass theorem to that idea of it. So maybe this is an idea we can go with. And so why do people care about that now? Well, it's been around for a long time, but one reason that I didn't write up there that people definitely care about is that we have really quite a lot of rather fast computers, so now we can do things that we couldn't do 4 years ago. But I think there's actually a kind of more fundamental reason, which is that we can start to think about doing, identifying general recursive structures in a data-driven way, and that is intriguing because it's kind of closing the loop on computing now. And if we can, so we've been generating recursive structures using programs that we rig up by hand, and then we've been kind of parsing special cases of recursive structures with parsers, but we haven't really closed the loop on this, and that would be intriguing if we could do that, if we could kind of generate something and compare it to information and then have a feedback loop in how we compute, because then we would actually get cybernetic computing. So and what are the prominent, important techniques that have risen to prominence in this iteration of things? Auto-associators are one of the most interesting classes of algorithmic gadgets that people have come up with. So they are basically that a concrete way of getting at that idea of what features are that I mentioned earlier. They are non-parametric models of spaces of joint variation, and the way that you get them is you have some hidden information that you allow your system to use to encode what it observes, and then it has to reconstruct what it observes from that hidden encoding of it. So this is kind of like an automatic form of data compression. You could think of it as that, where you've given your algorithm has this big space of joint variation that's its input, and then it has a smaller space that it has to use to represent as much information that it can use to reconstruct that. And some work on these has actually considered recursively composing them. And a lot of the thinking on this is still focused on finding some clever algorithm that is able to find a fixed algorithm that's able to find a model, but isn't too computationally demanding. But actually, this some approaches to this have actually used searching a more broader hypothesis space to do this. And one of them I saw did gradient descent, but it did it using this very general purpose information theoretic objective function that is a more direct embodiment of this like idea that I was just referring to heuristically before of compressing a space. So, and then another interesting thing, kind of the other main thing that has come to the fore, I would say, is recurrent nets. So this is actually a process where you have, as part of the dynamics, there's feedback. So LSTM, long short-term memory, is one example of that, and that was used to You can actually use that to learn fairly non-trivial, well, I mean, in a way they're trivial, but you can learn grammars that have really long state dependency. For instance, there's like the canonical simple example of a context-sensitive grammar is a language where you have this grammar that is A to the N, B to the N, C to the N, or something. Or these could be different, but you're going to see NAs and NBs and NCs, and that's the language. And if it's N minus 1 A's, that's wrong. That's not in the language. So you have to learn. You get a sequence of these things, and N could be a very big number. So actually, while you're going through this, you have to learn how to count in order to identify this grammar. So it isn't just recursive compositions of things in a context-free sense. You have to have this context, and LSTMs can learn one for like N is about equal to 50,000, which is so they can learn to count to 50,000, which is actually bringing a lot of context-sensitive complexity into the scope here. And further along in this direction, I think it was this year that came out, the reinforcement learning neural Turing machine. That was also very interesting. So that was first what they did was they just did the neural Turing machine, and that was a previous paper. So they just took a Turing machine and they made all of the discrete choices between two binary extremes into a continuous choice with a continuous parameter, and so you can linearly interpolate between the two ones. So like, and instead of your position, you get like, I might be botching the details a little bit, but instead of the head being in a definite position, you get kind of like that might be something that isn't seems actually, but the point of it was to get it so that you could train everything by gradient descent again. So you would, and for that you would kind of hope that you were in a nice convex space, but the whole point of a Turing machine is kind of to do really strong dependencies that result in really nonlinear behavior. So you're about as far from a convex space as you can get unless your underlying problem happens to put you in that subspace of Turing machines. So they've had some interesting successes in training these to do a few simple things, but it's not really clear that is going to generalize, because they're applying gradient descent to maybe the worst thing you could possibly apply gradient descent to, which is learning the dynamics of this thing with extremely strong dependencies on really long chains of states, and that's the whole point of the thing. So that might not be the way to go about it, but it's still I think it's definitely asking the right question. Let's get back to the 80s, and this was maybe the high point of research in non-deterministic computation. Was the 5th generation computing project of the Japanese government in the 80s, and there was maybe more political significance to this than academic significance to it in the end, oddly, but they were essentially building on Prolog, which was still not quite 10 years old at the time. Prolog is a language where evaluation is non-deterministic, but unfortunately involves an exhaustive enumeration of combinatorially exploding spaces of Boolean joint variation. So that is extremely inefficient, and so while in the abstract having non-deterministic evaluation could let you not focus so much of your activity on how evaluation needs to work, in practice this just gives you a different default mechanism that you have to learn how to work with to get to where you want to go. So you still have to bring this this knowledge of your problem that you you have to have in every other computing paradigm, which is that you have to know how evaluation should proceed, and you have to manually arrange for it to go that way. And so, kind of ironically, the worst thing about Prolog is its reliance on logic. So these discrete, especially if you're just trying to do it with like this fairly naive, like one-size-fits-all mechanism, a purely discrete combinatorially exploding state space is really hard to search. And I don't think they ever got into this question of like information feedback, because I mean, one thing, like floating point units are kind of a new thing for like a lot of hardware that people were working with, and also it just isn't really part of the paradigm as it's stated. I can only speculate, but for whatever reason that didn't enter into the picture, although those tools have come along since then. And so what we kind of ended up with, I mean, we didn't even really end up with Lisp, but that's kind of as close as we came to ending up with anything from all of this. And you know, Lisp still has its fans and is used to great effect occasionally, and so we could think of it as getting the non-determinism back out of Prolog and then just reintroducing it locally ad hoc. And that's not really historically what happened, but I put it that way because that is kind of what is happening now in these functional programming based probabilistic programming languages. So I think we're still seeing some of the aftermath of this. So yeah, probabilistic programming languages. I recommend the writing that Oleg Kiselyov and his collaborators have done on this. But he's actually pursuing, and he says so in one of his papers, this approach of having this mostly deterministic functional programming setting and just very carefully, tastefully introducing a little bit of non-deterministic evaluation and doing it in terms of probability theory so that it's still fairly narrowly constrained. So again, good for knowing a priori how your system is going to work, but bad for your system being able to cope with the challenges of an uncertain environment. Why might we not have to be that conservative anymore? Over the last 10-15 years, Monte Carlo research has risen to prominence, and we've gotten efficient ways of dealing with partially observable Markov decision processes and of doing global search in general. And that was what was holding these previous paradigms of non-determinism back. So, and a common theme in a lot of these is that we take partial information from a search in progress and we feed it back into the choices the search makes so that it can bias what it looks at based on what it knows so far. So this is a really important milestone in POMDPs. So this actually, I believe it gets rid of the exponential dependency on the depth, I think. It gives you much better balance on performance. And it kind of does it by, I think, determinizing the search at the first branching point at the first level. But in any case, this kind of changes the assumptions a little bit, and it blows through a barrier that is kind of part of the folk information of why this is hard. And also, with Monte Carlo's research and with some other techniques, approximate global optimization in problems of large or unbounded dimension that are NP hard is actually easy. So like NP is defined by making a definite decision about the absolute global extremum. If we allow ourselves to be approximate, that is often quite good enough, and then we can do much better, and we don't encounter problems that are nearly as intractable. So examples of successes there are the cross-entropy method, which has been used in both finite dimensional problems and Markov problems. And there's even success with just doing exhaustive search with a partitioning of the search space, but using interval arithmetic of some form or another rather than just looking at points. So instead of sampling points, you're looking at what interval does the solution lie in, and you're able to get a bound, and that actually will also make things much more computationally tractable. And some things that you can grab right now to do that are, well, unums is still kind of coming down the pipe. That's actually a proposal by John Gustafson, who's a high-performance computing expert. He's been looking at what's wrong with floating point and how to fix it. He's come up with his own very refined version of interval arithmetic and a way to implement it efficiently on hardware. But there's software simulations of it coming out, and I'm actually playing a little bit with that now. And part of what he develops with that is a methodology to do optimization and to integrate dynamics, solve ordinary and partial differential equations with search, and just iteratively refining the bounds until you get a really tight bound around whatever you're looking for, and it seems to work quite well. This is also in some physics packages I found, COSI Infinity and CXSC. So this is something that has already been working for many years in certain fields. But I think there's still a lot of fields where if you say something is NP hard, it kind of ends the discussion, and it doesn't seem like it should be doing that. The first question we should ask is, would an approximate solution be good enough? And I haven't yet found one where it would be. And a little bit further on in the within what's been going on post-logic programming, constraint solving has actually come into its own within the logic community. So G-code is an interesting package that implements constraint solving. It does it basically by this message passing methodology that where the implications of a constraint are propagated locally to the neighbors in a network of quantities that mutually constrain each other. And this is conceptually a very simple approach. It's pretty similar to what goes on in normal evaluation, except the evaluation can go in any direction instead of just a priori determined direction. It's very close to the actor model of computation if you apply it at really the lowest levels, and it achieves state-of-the-art performance on benchmarks and competitions. A drawback of this so far is that they actually got this by eliminating the recursion within the language. So you can only express a determined finite problem within the language. And then if you want to have, a new kind of constraint, you can't write that within the language. You have to drop down to the C++ that it's implemented in and figure out how to do it there. So that's actually a big drawback. It's not really going to be useful for general purpose computation that way. 2009, Sussman and Radul started to chip away at this with their information propagation framework. So now they are starting to be able to express unbounded recursion within the language. The main thing you have to do that, you need some way of representing an unbounded structure with just a finite number of symbols to do that. That's the fundamental issue there. So they came up with this idea of a switch, which is basically just something that monitors its local information environment, and when something passes over a threshold, only then does it instantiate what is beyond it. So that is that is kind of the most basic mechanism you could think of to defer instantiation of part of this unbounded space of constraints. And then they've also just made another interesting choice, which is to say that it is not just about representing a solution set, but it is about gaining information about a query. And so this is also another very important thing. So I'm actually, I found, excuse me, this is led in my own project to, I'm actually looking at quite different mechanisms for both of these things than what they used. But the two fundamental ideas are still there. And I think if you put these two things together with some of these efficient ways we have of searching unbounded spaces, then we could actually have, we could have a language that is at the same level of abstraction as SQL, but it is actually dealing with full Turing complete unbounded recursion, and there's a query planner that is reinforced by the events of accumulating information about a query there. So that's not what they did, not yet at least. They're still imagining that evaluation is going to kind of be under manual control, but these two mechanisms give the promise that you can move beyond that and actually finish the job on declarative programming, I think. And similar to what they did, but it was in the late 90s, I think, was Zdravko Markov's net clause language, which also is another mechanism for decentralizing evaluation by, and it's in a Prolog framework, and it also has these events where like there's this threshold that you pass and then it causes the unification of terms. So that's also another not quite as strong a step towards just the ability to deal with uncertain information declaratively, but also an interesting precedent. So, kind of been saying this already, but what might it look like if we started to put some of these pieces back together? So we would have an explicit query that is driving evaluation. Yeah. I think I could. This is almost the end of this, and then I was gonna figure out what to do next. So,
I'd like to hear it.
yeah. Okay. So, what if we had a language where we've got an explicit query, and there is the way evaluation works roughly is that there is a goal of accumulating information about it. And then we can use the idea of local information propagation, and then we can also build ways of doing that more efficiently on top of that. And so one of the most important ways of doing that, I think, would actually be to go grab these auto-associators. I didn't actually talk about this yet, unfortunately, but so a lot of where auto-associators come from is theoretical neuroscience and studies of animal visual systems, where, and this is also where you get a sense of how they might be recursively composed, is that in the visual system, in the layer of the cortex that's closest to the inputs from the retina, let's say, you'll just see very simple edge detectors, and so they learn to recognize the most prominent statistically patterns of joint variation that they see, and what those are kind of like uniform regions of stimulation and edges. And then on top of, the next layer up gets that representation, and then when you poke that, what you see, or when you show it something and when you see that it's firing, so, and I think you can also poke it and someone will see something, but that's harder to do on an animal because you can't usually ask the animal what it sees, but you can show it something and you can see if something is firing or not. So that's what they did. That was Hubel, and recently got a Nobel Prize for doing that with cats. And then so the next, so the first layer has got this representation of uniform regions and edges, and then the next layer up will have simple curves and shapes that are built out of that, and then maybe the next layer up is starting to see textures, and it's recursively composing these local patterns of joint variation to get at this multi-scale structure in this big combinatorial space of possibilities. Otherwise, it makes it look less like a combinatorial space because it's actually only focusing on the statistically significant patterns of joint variation within it. So one of the problems we have in search-based evaluations is we have these huge, exponentially or combinatorially exploding spaces that we have to search. But what if we compress them this way? So yeah, I think that is what we would get. We would be able to do general purpose computation, but it would be driven by a query and query planner. It would have a goal of accumulating information. The space that it's searching could be of the size of the information content of the problem instead of just enumerating everything without any information about what is significant and what is not. And everything is built on this lower level foundation of local message passing. So this is something that should be straightforward to map onto parallel hardware, and it could actually give us a way to exploit that, since we don't really necessarily know how to do that yet in general. So what might then come of that? So if we can, so a little bit of programming languages jargon, compilation is usually what people call a strongly constrained deterministic process of mapping a source program onto an object program. Synthesis is the term if you allow yourself to use non-deterministic search. So if we had much more powerful ways of doing that, then we could rely much more heavily on it, and we could probably much more easily adapt to whatever computing environment we're in without having to manually work out how to exploit it ahead of time. Also, we can defer a lot of the control decisions that we would have to make at definition time to runtime, and then that would make everything adapted on whatever the regularities in the input data would be. It's possible that garbage collection could be simplified because it's happening at this higher, more semantic level. We could take a legacy program and parallelize it by looking at the source program, taking the logic component of it, ignoring the control component of it, and then querying for its observable behavior. So if you have like a C program on Unix, parse the C, ignore all of the calls to the threading library except as they set up some sort of a pattern of communication, but don't worry about the scheduling. Query for what system calls it makes, or a certain subset of those that you care about, that's its observable behavior. And if we have kind of a sensible prologue-ish tabling or caching of our work so far, then we can get everything to incrementally recompute in response to changes instead of doing everything all at once. So that just kind of follows from pretty well-established tabling approaches. If we've built uncertain information into the semantics of this, then if things are uncertain, we should be able to get bounds or uncertainty estimates on everything. So the whole slogan for this becomes, now that we've kind of closed the loop on how we deal with recursive structure, and we can identify recursive structures, we can more rigorously characterize how they work, we can generate them, we can search them. And so that is actually a problem of that type, was how I got into trying to put all of this together, was that I was looking at smart contracts, and that is a situation where you have something that is essentially a computer program, but it could depend on uncertain information, and you want to be able to work rigorously with it. You want to be able to do projections of how it's going to work under certain financial assumptions or You might want to bound your risk under it because it's an adversarial thing. So that was what got me thinking along the lines originally with smart contracts. But then there's kind of a broader human benefit to it, which is that you could have a combinatorial reduction in the work that the human does to create software. So here there's a seminal paper in logic programming by Kowalski, which is program equals logic plus control. And so logic will just in the broader sense of like the animus of the problem and not necessarily Boolean logic. It generalizes, even though that Kowalski did have Boolean logic in mind, I think. But that the logic is just a set of relationships that apply in the domain, and then the control is the specific sequence of inferences that you do with those relationships to inform yourself about the question you're asking based on the facts that you have. And so there's this graph, and then there's all of these paths through the graph that you could take. So there are combinatorially more paths through the graph than there are nodes and edges in the graph. So, and that depends on your problem, of course, but just in general, that's roughly what you should expect. So, if we can get this to work, then we really are in the declarative world, and we can only deal in terms of the logic. And then the control actually gets discovered adaptively when it's as constrained as it possibly can be by the actual data that has come to it. So I think we are the agents in the middle of this bow tie, and software is this thing that is supposed to be bicycles for our minds. So if we got this actually working, then I think we would get a lot more leverage, and the center of that bow tie would become a lot broader, and then a lot more people would have access to a lot more possibilities, and maybe also we could get more rigorous answers to these, to like the scientific questions that were coming up earlier, where we're kind of like stuck making too many a priori assumptions, and it's very misleading, and the results are very simple. So anyway, that is all that I've prepared for the slides, and I'd like to thank the organizers again. I was trying to figure out what I would do next now, and one thing could just be a standard Q&A. Another thing is there are a lot of things that I really like eased past in like the technical aspects of this, because I didn't know how much the audience would be interested in the technical details of all of these techniques that I've mentioned. So I could go more into that, and certainly if there were kind of a more open-ended discussion around these themes, I would welcome that as well. So I guess that'll be the three alternatives I'll propose, is like standard Q&A, or like more whiteboard-driven explanation of how some of these mechanisms work, or like a general discussion and throw shares and stuff. And so,
Yeah, well, you've given a lot of high-level discussion of a lot of things, and so if you maybe give a detailed description of what you were specifically working on, or your motivation for the small, what's most exciting for you, where you put your time?
Oh yeah.
Could you explain that in more kind of concrete detail than
Yeah, okay, maybe that's what Ken was getting into. So this is a big space of possibilities to be considering, obviously. So a lot of what has been a minor obsession in the last couple of years is actually reducing this to like a concretely implementable agenda. So the way I think that looks so far is that there is something like a prologue-ish interpreter at the center of everything, because that lets you do that lets you do unification, so you have a nice way to like look at a symbolic expression of a relationship and then build another relationship out of it. So, and fundamentally what that's doing is that's representing a joint relationship among things in terms of, just in terms of, you know, a discrete structure, logical structure, but then if you have a way to describe numerical computations on top of that, then you can unify something that is approximate with that, and then you can have the approximate version running alongside of it and tabulating what happens in this joint space. So then you can stick you have a very nice mechanism for like gluing your auto associator to your grammar rule, for instance, and also then once you know like which grammar rules refer to other ones, then you can kind of hierarchically compose them, but it's in a way that is still driven by the distinctions in this framework that supports Turing complete unbound computation. And then beneath that, it also becomes easy to find some base case and some composition of base cases that you know how to express as like a data flow kernel that you could then go and translate into like some OpenCL code, for instance, that carries out that data flow. So for now, I should go more, I think to get into that, I should go more into how information propagation works, and then this will make more sense. So like Radul and Sussman, their information propagation is basically message passing. It basically lives right on top of the actor framework level of abstraction, but is making specific choices about what the actors are and what they, what their job is in all of this. So it's kind of saying like actors are there to accumulate information about some value they represent, which is basically some dimension in a joint space of variation. So, and the way they do that is by default they pass messages to their neighbors that enforce that constraint in the local way, and then if you can assure that you have non-monotonic, or if you can assure that you have monotonic accumulation of information in that, then eventually that process should converge to the maximally constrained set of relationships that you have given the facts and the relationships. And so what you have is you have this when a fact impinges on a relationship at a certain point in this graph, it starts sending messages to its neighbors, and then what is neighboring to it is determined by what sort of a recursive rule structure you've built up, and then the messages spread from neighbor to neighbor until they are redundant, and then propagation stops. And some of these chains of messages will reach all the way to a query node, and then that is actually telling you about your query. So there are already some, I am tempted to make analogies to how neural computation might work in a loose sense here, and I mean, that could be a whole other discussion, but at most, I think it's kind of like a loose analogy, unless you can find better evidence for the biological side of it. But basically, and that's what Markov's project was really focusing on, that aspect of this kind of evaluation, where you have like the accumulation of a significant amount of information that then gets passed on. So you're ending up with these chains of messages that depend on each other, and you can throw them on a message queue, and then so you can have a bunch of threads with a bunch of message queues on them that are processing out these chains of inference, and then in a similar way to how in a VM you're sampling the stack to see what the hot code spots are, you can sample these message queues to see what the hot information propagation paths are, and you can take those. Those are all, no matter what you build on top of them, those are all boiling down to these simple local arithmetic and logical operations. So you can find what the ones that are the bottleneck are in your computation, and then you can take those out of off the CPU and maybe map them onto your GPU by writing a kernel that does those composed operations, or whatever other weird hardware you might have. So that is kind of how the system looks at the low level. How it's actually taking these ideas and running them and doing it in a way that is not insanely expensive. But I don't know if that's getting at the specific part of like what you were asking about, Ken, or does that help you to get a better sense of what you wanted a better sense of?
You've written up any of your projects as reports about it?
So I actually, like the key part kind of came out of theoretical neuroscience. So I was aiming at that community, and I wrote up a draft and I submitted it to a conference, and that, like, 2 reviewers said it was interesting, but it wasn't really theoretical neuroscience, and then the 3rd reviewer said I don't get it at all. So then I started talking to the programming language people. They like it much better. So what I'm going to be doing so there's a draft up on arXiv now that is kind of from a perspective that some knowledgeable people found a little bit unapproachable. So it's there, but it might not do the most that it could for you. But in the near future, I'm looking at both academic and commercial options of moving this forward, and it seems like maybe the academic programming language research community is the right way to pursue this, and that is going to lead to more work and more publications describing that work, probably. Still have to see exactly what develops. And what I'm working on in the short term actually has to do with that, where I'm going to be getting a prototype together and actually running, and then make that part of my part of the package that I use to figure out my next steps.
Could you mention again what particular data sets you're thinking of applying methodology to? You're talking about something financial, I think.
Okay. Well, my original motivation was with smart contracts, which is where you basically have a computer program that is going to make its own decisions about financial transactions and go and carry them out automatically. So,
what would be an example of that?
Well, people, I think in the smart contracts community, people are interested in, I think a lot of what they're interested in so far is fairly simple coordination mechanisms, where like you could do something like an escrow, where people, people have this decentralized intermediary free, or the intermediary is the system that will wait until certain conditions are fulfilled that provide evidence that a sale has taken place with no problems, and then it will move the money. or something very simple and rigid like that. But another thing that is quite possible is if you could kind of have trust in a system that could make more complex decisions, then you could do something like creating financial options comparable to the ones that we have already, that are dealt with in an ad hoc way, and there's kind of a lot of opportunity for obfuscation and fraud and how that's dealt with. But and there's a company in France that has built a package that is roughly of the same scope as this, but is using a lot more mainstream techniques, but is also letting you formalize a contract and then evaluate it under probabilistic assumptions about what the market's going to do or something like that. That is not really what I'm mainly interested in anymore, because I found it really, I'm not personally too interested in it, and I found it kind of difficult to make the case that this would be valuable to people who already mainly have access to high-end tools that are built in a lot more complicated way, but in the end kind of do the same job, and they already exist. So I am actually now, I think a lot of it comes back to my roots in control theory, where you have techniques that are adaptive and can do a very good job in finding actions for a robot to achieve a goal or something like that, but they only deal with the mathematically tractable, like, convex cases for the most part. And I am interested in maybe expanding beyond that and connecting up with some other current research in robotics to make these more open-ended situations tractable to deal with. And I think that is, part of what probabilistic programming is doing now, is it's getting into like modeling linguistic uncertainty and communication and coordination problems. So I think it would be interesting to bring an even more powerful tool to bear on that sort of thing. And beyond that, I don't know, in a sense, because the more I look at this and the more I connect it to just fundamental programming language theory, the more it just looks like the way all software should work, and you can do anything with software. And of course that's not helpful to anyone to say, I want to do what software does. So, but that is kind of what it seems to amount to.
Yeah, sorry, I was just looking at the. Thank you. Join me in giving Anthony a hand. What I was looking for was the